Hi, everyone. I am the only person standing between you and the lunch, so let me get started. As she said, I am a Zenodia Charpy. I'm a senior deep learning data scientist working at NVIDIA. Today, I'm going to talk about a very novel technique called p-tuning. It is a parameter efficient tuning technique to boost LLM, stand for large language models performance. Now, before we diving into that, I'd like to tell you about what you probably have heard of in the previous sessions of the movement that's happening here in Sweden. Now, through the collaboration between AI Sweden, RISE, WASP, Vara Media, and Language Research Arena, as well as NVIDIA, the fruitful outcome is as you can see on the left-hand side. There's a series of foundational models of varying sizes that you can see on Hugging Face. Now, in order to access these models, you will need to apply for early access, which is the link over here on the right-hand side. Now, I do talk about foundational models. Want to make a distinction so that you know it's clarified. Foundational models are not tuned or aligned to human preferences such as ChatGPT side. If you are interested in exactly how you do that through InstructGPT as the first stage, talk to me afterwards. But this is not this talk about. We are going to talk about foundational models. Foundational models do need tweaking, and those tweaking, we need to have educated guests. And let me briefly walk you through those educated guests one by one. First, we need to understand model sizes and tasks. As you can see in the previous slides that we do have a variety of model sizes of the foundational model here in Sweden. And as a rule of thumb, the larger the model, the more downstream tasks it can do in the zero or few-shot learning context. In the inference runtime, however, one still need to tweak the hyperparameters. What do I mean by them? For example, temperature, top P, top GAIA, random seed, beam search size, and so on and so forth. These are the hyperparameter one need to tweak in order on a per task basis. Now, after you have understood these, then prompt engineering become fairly important. Now, if still for a simple classification task, let's take that as an example. After you have understood this and this and this, and you have tried and errored for several iterations, it still didn't give you the performance that you needed, then it's time to find some parameter-efficient customization technique, such as p-tuning. Now, p-tuning is not the only technique. However, that will be our focus for today. So what is p-tuning? Now, before I dive into the technical aspects of p-tuning, let's take an much more intuitive examples. Two person, they're a couple, walking down the street. And the woman said, "Oh, it's snowing, I'm cold." And look at the guy. And the guy was like, "Yeah, okay." And the woman say, "Read between the lines," angrily. Read between the lines. A lot of things can be said in this scenario. However, the guy still didn't understand. That's why he said this. So, now p-tuning explicitly exploit the read between the line. There's a lot of things can be said in this scenario. It can be, "Would you like my jacket? Are you okay? Are you cold?" Any of those would be fine. However, still, one still need to tweak the optimal way you query the model in order to get the optimal response. That's p-tuning. Now, I did said that the way you query the model matters. As we can see, if you construct a question in different way, your top one accuracy vary quite a bit. Now, language models, they don't just eat a sentence directly. It breaks a sentence down to tokens and they exchange each tokens to an integer, a discrete number. So p-tuning is exploiting the in-betweenness. What do I mean by that? More concretely, it exploits the virtual tokens, which are floating numbers in between 0 and 1, in between 1 and 2, in between any of those discrete integers. That's how it exploits the in-betweeners, the virtual prompt tokens. They are floating numbers. You insert into your questions template as well as the context before you got the answer. That's how it exploited. I did say that p-tuning is a parameter efficient technique. Now let's take a look at that. Taking a GPT-3 model, a 3.6 billion parameter. Again, this is Swedish. You can see that right here and right here, it's non-trainable. So the language model is frozen. P-tuning is a two-layer LSTM neural network that you use to produce the virtual prompt token. Again, the virtual prompt tokens are floating numbers that you insert into your template of the question you asked. Now, it will automatically, because it is a neural network, so you can tweak it in order to find the optimal in-betweenness to ask the question to get the optimal response. It is parameter efficient. As you can see, it will only take 132 million, order of magnitude smaller than the 3.6 billion of the parameter, which is frozen, for you to tweak the 132 million to get to the optimal response. Now, before we talk about that, we have to talk about the data set. You know, the experiment comes with the data set. Now we have the model from AI Sweden. You just have to apply the early access, right? Now let's talk about the data set. Unfortunately, here in Sweden, we do not have Big Bench like. Big Bench is from Google. It's a data set that you used in order to exploit, to figure it out if the large language model indeed can do a variety of downstream tasks, how much it understands, what does it understand, what category it understands. That data set is a benchmark data set called Big Bench. We don't have this in Sweden. So because of that, we need to get creative. The data set that I'm using is called Finance Open Mining Question and Answer data set. And this particular data set is a binary sentiment analysis data set. So given a sentence right here, it will either be positive or negative. However, since I'm saying we're going to get creative, we're going to translate this to Swedish, and automatically the binary class grow to be 6 class. Why? Because in Sweden, we have all this positive has 3 forms, negative has 3 forms. So together they have 6 class. So the complexity grow. Okay? Now we know what data set that we chosen because this is an easy data set. That's the reason why I chose it. But it also works, p-tuning also works for any other data set as well. So the experiment comes like this. Let's first contrast the workflow of English versus Swedish. The English workflow, you just pull down any benchmarkable data set which established in the English ROM. That's easy. And you do p-tuning. And you compare if p-tuning is better than the benchmark given accuracy or whatever matrix that's using. For Swedish, we need to first do translation before we prep the data set for p-tuning. So let's take a look at the translation workflow. First, I chose to train an English to Swedish translation model from scratch. Why? Because, well, we do have a lot of like Google Translate, Bing Translate, and what have you. However, they always comes with the upper limit roof of free quota. So you're going to get error timeout for the reason that you didn't pay. So I decided that, you know what, I'm going to train my own English and Swedish translation model using Ompus data. Ompus data set is a parallel corpus that is already known for its quality for Swedish, Norwegian, as well as Danish. And you can also look at it yourself on their website. After I have trained this model, I have translated the finance FYQA sentiment data set to Swedish. Then we went through that quality check. So what do I mean by quality check? That, translation usually might have a bad quality. You have native English and Swedish speaking persons. We have a lot of them here at NVIDIA apparently. So I ask them to help me to manually sample from those data, translated data, comparing to the English original to actually check whether this is okay or not. If they are not okay, I drop them. Okay? Then after filter and modify all this corrupted translation, because sometimes they do have the time to actually manually translate it so that I don't have to drop them and so on. Then I divide it into tenfold. So it's a tenfold cross-validation, which means that I'm going to train 10 p-tuned models and then average the result. The prepared data set is fairly simple. You're just going to have to dump it into loose JSON format. Now the p-tuning is that you select a fold. So you start with the 0 fold, Python index start with 0, and then you search for hyperparameters because it's a neural network, it has hyperparameter. Then you train a prompt encoder, which is 2 layers LSTM neural networks. And then you use the training validation data and you held out the test data. And then you will have a model which you use for prediction. Again, because I want to translate it backwards to binary data set, I need to do the remapping, which we're going to talk about in the next. So what is the result? Before we talk about the result, we have to talk about a problem. Because we don't have the benchmark equivalent of this data, we cannot use the English benchmark. It's not fair. So I need to establish a baseline. So how do I do that? Now, foundational models should already know some sort of capability to do these downstream tasks. So I use 0 few shot, which I mentioned previously. So apart from the 0 shot, which we're going to take a few examples of why it doesn't work well, we can see that for 1 shot, 2 shot, 3, 4, 5 shot until I go OOM, the performance of the classification is around 42 to 51. So that's my baseline. So p-tuning should do better, right? So as I said, large language model, especially this type of foundational model, auto-regressively, when you give it a sentence, it will just try and continue the sentence, which has nothing to do with the ground truth of sentiment classification which you wanted, as you see. That's why 0 shot doesn't work well. So what is few shot? So 1 shot is you give it an example and say, this is an example, and this is the ground truth I want you to classify. Then now I give you another example. Now do this classification. That's 1 shot. 2 shot is that you give 2 examples and you say, I'm gonna ask you again because you have seen 2 examples and so on. Okay, so now we have our baseline. Remember, that's what? 42% to 51%. Then we should do better. Before we recalculated the, again, because the previous one is also done by remapping. So we need to check that all of these are mapping backwards to this. And all of these is mapping backwards to this. So we're going to shrink the classes from 6 to 2. So it's again binary classification. So after the remapping, let's take it all tenfold and then the average. So it's like this, and the average score is 82. So it's almost twice as good as the few shot learning. Now, let's talk about summary. What have we learned? We do have a bunch of foundational model of varying sizes, which you can, if you want to, apply for early access, and then you will be able to access their private repo on Hugging Face and download the model checkpoint. We adopt the English workflow, just add 1 translation from English to Swedish of the benchmark dataset. Then the rest of the workflow is the same. However, you are limited by the translation quality, so you do need to be vigilant about that. If you have any other questions, and or if you want to see exactly how to do this, I have actually written a blog detailing the exact workflow as well as more technicalities and the code base, as well as where you can get the model on this blog. That's it for today. Thank you.
Thank you very much. I'll actually be very arrogant and take the first question. Sorry, it's not directly related to it, so please ask also your questions. But I see in your bio that you are interested in grounding the factual correctness of large language models' responses, right? So the panelists before, they dismissed my question about factuality. I don't know if you noticed.
Yeah.
Can you just spend 30 seconds to tell me why do you think that is important? Or anything about it?
I can actually say more than that. So I don't know if you guys actually read the paper. It's called Retrieve from Trillions of Records. So in fact, there is a movement. So large language model, everybody knows, hallucinates. And the hallucination can be grounded by retrieval type of model. What do I mean by that? So a transformer model has key query value pairs, and then it has the multi-headed attention. If you don't know what that is, it doesn't really matter. If you're thinking about these key query value pairs, they are information retrieval mechanism. The way it works is the following, that you given a query, then you find similarity search in your databases, and then you say that, okay, these are the information that I needed, so I retrieve the top K nearest neighbor. Yeah, that's how you do that. Now, retrieval is similar like that, but when you train autoregressive model like that, but you need to do a technique to the database, and the database you do is that you vectorize it. You can use any model, like BERT model, T5 model, what have you. What it come out of it is that it will gonna give you a key query value pairs. It give you a key query value pair because you have a BERT model, right? You take these key query value pair, you bind it with the multi-headed attention, which also has key query value pair. Yeah? And then you re-rank it, you weight it. And then in the inferencing, when you train this model, when you're inferencing runtime, you can say, because of this record in that paragraph, that's why I make the prediction. That's how you ground its factual correctness. And this movement right now has been tested out. I'm not saying it's perfect. I'm just saying that there are papers and technique and implementations that's been actually done in order to address to this particular hallucination problem.
Thank you very much.
Yeah.
I appreciated this. Do we have questions from the audience?
I'm talking too fast, aren't
I? Yes, we have a question there. But usually we appreciate very much when the speakers take the right time, so nobody's stressed. So that's really good.
Thank you.
Hi, thank you for the great talk. So could you say something in terms of comparing this P method with, or prompt engineering method with, let's say, optimizing some sampler on the end task instead? Because I guess you could either align the prompts or align the sampling method as you do with reinforcement learning, for instance.
So if you're talking about InstructGPT type or ChatGPT type of model, that's something else. So if you actually look at the InstructGPT paper, it looks like this: that you have step 1, you have supervised fine tuning, which means that you have to have labeled data, and then the second part is that you have people interacting with the large language model, and then you edit the response. You say that this is not the response that I like, and so this is what I think is the best response you can possibly get. So from that, you will get signals of what human preferences is. And however, for neural networks to understand this, you need to construct equivalent reward model. So for every query that you have the human edit with the response, you need to have this reward model that still need experiment in order to make sure that it's aligned with human preferences. Once you got that, you can very happily go on to do your reinforcement learning with human feedback, and then you get your ChatGPT.
Yeah, my question was more related to, so for instance, for I mean, if you look at these rule-based reward models, for instance, they are not strictly a reward model in themselves, but rather using the original language model to actually set up a number of guidelines similar to what you explained here.
No, this one has p-tuning did not interact directly with the model. So this particular mechanism. P-tuning has two versions. One is the p-tuning v2 versions. This is the v1 version, version 1, which means that again it only interacts with your input by inserting virtual prompt tokens. It does not interact whatsoever with your large language model. So the input, when you go through the large language model, the model is frozen, and then the response will go back there. And then reinforcement learning with human feedback actually interact with the model itself and tweak it.
Yeah. Maybe I can continue the discussion afterwards. It's getting a bit long-winded.
So. We have another question down there.
Go ahead.
Thank you very much for the talk. The translation that you picked up, the Opus model, are there any characteristics of that model that are seeped into the p-tuning? What I mean to say is that what if my translation was only for a particular domain? Will I have a better language model in the new language that is more suited for this particular domain?
Can you say that again? I'm not sure I understand.
For example, if the translations that I had, the Opus, I only have medical dialogues in it. And now I want to see, would that affect in any way the kind of language model that I will get in the end?
Okay. Things that I probably didn't say is the following. That, again, large language model, not only by its sizes, as well as the data it's trained on. So if you have domain shift, which is data shifting problem, the underlying data that the model trained on has a lot of say in what a model can or cannot do. I give you an example. If you, I recently helped another influencer, we call them, train a language model that composes music. So he can co-compose the music. And so he's, in that domain, fitting the language model to music tokens. Now, thinking about this model, do you think, show of hands, this model will understand human language? Show of hands. Yes, no. Yes?
Yes.
No? Yeah, no. It doesn't. So what I'm trying to say is that domain adaptation is another problem itself. Whereas even though that the model usually when trained on gigantic corpus should already know some parts of it because you have a lot of paper, medical paper and so on and so forth, which you could potentially maybe understand. But recently, for example, that I have tried and p-tune a model trained on, it's a very large language model. It's the size of 43 billion. Then you fit that to a medical chemical compound domain in order to, find drug discovery, not gonna work. So yeah, it has this limitation, absolutely. The foundational model needs to already know that domain. Does it answer to your question? Very good question.
Do we have other questions for Zenodia? But then, oh yes, we do. I'm very sorry.
Hi, thank you for the presentation. A question. Why it was chosen to use an LSTM?
Yeah, that's actually a very good question. LSTM is just because of its fact have the ability of keeping the memory bank. It is indeed a problem when you increase the LSTM to like 3 or between 3 to 5 layers, and then you would have, quite hard time to control the gradient. So the chosen LSTM to be layer 2 is because of that. So very good question.
And just a follow-up.
You can replace it with any other things as well, by the way.
Did someone try with another transformer?
Yeah.
Okay. Does it work better?
Not really. In fact, we actually check it out. If you use adapter, so adapter is this bottleneck kind of architecture you insert into the transformer, actually work better than if you replace LSTM with transformer.